We present depth-aware image-based neural radiance fields, short DINER. Given only 4 input images, we predict a volumetric scene representation that allows us to render the scene under novel views. Specifically, we predict depth and feature maps from the input images and propose novel techniques to use that information during rendering. Compared to other methods, DINER synthesizes also extreme facial expressions more faithfully and reconstructs fine details better. Since depth maps are not bound to specific object classes, we can also evaluate our method on general objects. We observe that in this scenario, DINER estimates the scene geometry more plausibly and solves major artifacts during novel view synthesis. Ghosting effects are reduced and high-frequency textures are reconstructed more accurately. DINER builds on top of PixelNerve, which we briefly review here. The input views are processed with a convolutional encoder to extract feature maps. The resulting feature maps are placed in 3D space. For rendering a target view, rays are cast into the scene along which query points are sampled. The points are projected onto the source camera planes to interpolate a feature vector. The result conditions an MLP, which regresses intermediate feature vectors. The vectors from all views are averaged, and a second MLP regresses the color and optical density of the sampling point. Volumetric integration yields the final color. During training, the L1 distance between predicted ray colors and ground truth pixels is minimized. Our method, DINER, builds upon this pipeline. As a first step, we add depth awareness. We employ a state-of-the-art depth prediction network to regress depth maps, including standard deviations and expectation values. For every sampling point, we determine the difference between the projected depth value and the sample location. The result is used as an additional conditioning to compute the intermediate features, which are then used to regress colors and optical densities. As a result, we observe improved geometry and higher synthesis quality. Adding a perceptual loss to the objective function improves high-frequency details. We noticed that artifacts occur in regions that are not visible in the source images. For these regions, the sample points project outside of the source feature maps. Previous methods apply border padding in this case, which results in constant values irrespective of the distance to the camera plane. To solve this, we propose adding border padding to the source images prior to the feature encoding. We also use positional encoding in the padded regions as additional input. The resulting feature maps span a wider range than before and provide distinctive features even for samples that do not fall onto the camera plane. As a result, the observed artifacts are effectively reduced. Finally, we improve sampling efficiency using the predicted depth maps. We aim to maximize the sample density around regions where rays intersect with the object surfaces, since these regions contribute most to the ray color. The estimated depth and standard deviation maps define probability distributions for where object surfaces lie. This allows us to determine the surface likelihoods of every sampled point with respect to each view individually. We apply max pooling to obtain view-independent likelihoods, and then shortlist samples with the highest values. To increase the sample density around the first ray intersection, we first calculate occlusion-aware likelihoods, then fit a probability distribution, and sample additional points accordingly. As a result, the synthesis quality around thin surfaces like ears improves. We compare DINER against state-of-the-art methods for the task of novel view synthesis of human heads. IBRNet, a model that blends the source images directly, can reconstruct high-frequency details like text, but blending artifacts occur which cause a high identity gap. PixelNerve reconstructs a more accurate head shape, but produces blurry results. KeyPointNerve, which leverages facial landmarks to guide the reconstruction, synthesizes high-frequency details better, but distorts the head shape. Our method reproduces the target identity more accurately than all state-of-the-art methods and outperforms them in terms of high-frequency details. Even for large viewpoint changes, our method produces images with high visual quality. Even for samples that lie outside of the training distribution with different ethnicity and other headwear, DINER synthesizes plausible results. Note also the high temporal stability for continuous sequences despite DINER being trained only on static frames. Thanks for watching.